Verlet integration is a fantastic tool to easily simulate simple physics interactions. In the video I did to demonstrate how easy it is to create a very basic physics engine, I used the naive algorithm to find collisions between objects. This allowed to handle a few thousands objects at a reasonable frame rate, but what if we want to simulate way more? In this video, I will present a simple way to greatly improve the performance of the simulation. This is the technique I use in all my projects involving physics, be it Verlet integration or impulse-based solvers. The aim of the simulation is to minimize the overlaps between objects. Two objects overlap if the distance between their centers is smaller than the sum of their radius. The value of the overlap is computed by subtracting the distance between the objects from the sum of their radius. Then, we move them along the axis defined by their centers. Each object is moved half the overlap. Here is an illustration of this principle applied to multiple objects. In this example, the initial overlaps were quite important. A single iteration is not sufficient to fix them. We can either perform multiple iterations, or we can try to minimize these overlaps in the first place by using substeps, resulting in much smaller objects' movements between physics frames, and thus much smaller overlaps. All the simulations of this video will be using 8 substeps, meaning that the physics solver will run at 480 Hz. This is how I enable substepping in my code. The naive way of detecting overlaps is to iterate on all the objects and, for each of them, to iterate on all the others. Check the distance and move them apart if they are too close. While valid, this algorithm is very slow because the number of checks to perform is equal to the number of objects squared. This algorithm could be written like this. Let's run a simulation where we continuously add objects and stop it as soon as the frame rate drops under 60 FPS, and see how much objects it can handle this way. As you can see, the simulation can only handle a few objects. What's really inefficient with this approach is that we perform a lot of useless checks between objects that are very far away. In order to vastly reduce the number of collision checks, we have to introduce the notion of space partitioning. One of the simplest structures is the fixed grid. The simulation space is divided in square cells. For maximum performance, I will use objects all having the same radius, and set the cell's size to the object's diameter. First, we have to add the objects into the grid. To do so, each object's index is added into the cell above which its center is. At the end of the process, each cell stores the list of its contained objects. Then, to find collisions, we iterate on all the cells and compute the distances between all the current cell's objects and the ones associated to the surrounding cells. To remove any boundaries check, we don't iterate on the cells on the border. This algorithm could be written like this. let's run the simulation again and see how much objects this new algorithm can handle. It's already much better. The simulation can now handle around 16 times more objects. We can improve performance further, as we will see later. But now that we can run bigger simulations, we can have some fun, taking advantages of very powerful characteristics of these simulations. They are deterministic. This means that a specific initial state will always produce the same results when the simulation is executed on it. With more objects, we can animate the creation of an image. To do so, we execute the simulation the first time, see where each object lands on the picture, and assign them the color of the underlying pixel. Then, we rerun the simulation with the objects having their colors set. Since the simulation will always produce the same result, all the objects will return to their previous places with the right colors. Et voilà! We have a very nice chicken. Thanks to modern hardware, we have a lot of cores that we can use to speed up our computations. Even if we drastically improved the collisions detection stage of our simulation using fixed grid, it's still the most time-consuming part of the solver. One straightforward way of multi-threading the simulation is to split the collisions detection by dividing the grid in several parts and assign each one a thread. With 2 threads, it would look like this. Let's check the performance with 10 threads. As you may have noticed, the objects are sometimes acting a bit like a fluid. This is because friction is not taken into account in this very simple solver. Using multi-threading, we multiplied the number of objects by 5. Now that we have more than 100k objects, let's try to generate a high-definition chicken. We start by running the simulation, set the colors of the objects, and run it again, just as before. It seems that we got a very nice KFC chicken, but that's not exactly what we wanted. The problem here is that data races occur when multiple threads are working on the same cells at the boundaries of their zones. To fix this, we separate each thread zone in two and solve collisions in two passes, ensuring that no cells are being processed by two threads at the same time. With this change implemented, let's run the simulation again and see if it works. This is much better. And that's it, we now have a deterministic multi-threaded basic physics solver